A cursor-based linked list, sometimes called a cursor implementation of a linked list, is a technique used to simulate the behavior of a pointer-based linked list in environments where true pointers are not available or not allowed. Instead of storing memory addresses like a traditional dynamic linked list, cursor-based linked lists use array indices, called cursors, to represent links between nodes. This structure functions similarly to a static linked list, but it is organized around a central array known as the cursor array, where each element acts as a node containing both data and a cursor field, the index of the next node. This method is especially useful in languages or systems that lack pointer support, such as early versions of Pascal or restricted embedded systems. Cursor-based linked lists allow programmers to enjoy the advantages of linked lists: dynamic insertion, deletion, and flexible node ordering, while relying solely on arrays to manage node connections. To build a cursor-based linked list, we begin by defining a static array of structures, usually containing two fields: the data field to store the value and the cursor field, next, to store the index of the next node in the logical sequence. The entire array serves as a memory pool from which nodes are allocated and deallocated. Initially, all array elements are linked together to form a free list, where the first unused element is pointed to by a global variable called avail. Each free element's cursor value points to the next unused element, and the last free element has a cursor value of 0 or -1. Depending on implementation, a second global variable, head, stores the index of the first active element in the actual linked list. When the list is empty, head equals 0 or head equals -1. This setup ensures that the structure can track both free and used nodes efficiently without using dynamic memory allocation. The process of allocating a node from the cursor-based linked list begins with checking whether the free list has available space. If the avail index is 0, the list is full and cannot accept new nodes. If space exists, the index stored in avail is taken as the new node. The avail pointer is then updated to the next free index, retrieved from the cursor of the allocated node. After allocation, the node's data can be assigned, and its cursor field can be updated to connect it to the main linked list. Similarly, when a node is deleted, its index is returned to the free list by linking it back to the avail pointer, maintaining efficient memory recycling. This allocation and deallocation mechanism mirrors dynamic memory management but remains completely pointer-free. Insertion into a cursor-based linked list depends on where the new node is placed. To insert at the beginning of the list, we allocate a new index, store the new data, set its cursor to the current head, and then update head to the newly allocated index. This operation is efficient and runs in constant time. Insertion at the end requires traversal from the head index until reaching a node whose cursor is 0 or -1, indicating the last logical node. After locating the end, the cursor field of the last node is updated to point to the newly allocated index. Insertion at a specific position involves similar traversal until the correct location is found, then adjusting cursor links so the new node fits into the chain. The array index serves as a surrogate pointer, allowing link manipulation without pointer arithmetic or address referencing. The search operation in a cursor-based linked list behaves like searching in a traditional singly linked list starting from the head index. Each node's data field is examined sequentially, and traversal continues by following cursor values until the target value is found or the cursor value becomes 0. Searching has linear O(n) time complexity because each node must be accessed in order. One notable advantage is that cursor-based lists provide good memory locality compared to pointer-based lists. because all nodes lie inside a contiguous block of memory. This can sometimes lead to faster traversal due to caching benefits, although it does not eliminate the O(n) nature of the search. Deletion in cursor-based linked lists follows the same logic as pointer-based deletion, except that indices replace pointers. If the node to be deleted is the first node, deletion is simple. The head is updated to the index pointed to by head's cursor. To delete a node at any other position, traversal is required to locate the node preceding the target. Once this node is found, its cursor field is set to bypass the node being removed. The deleted node's index is then returned to the free list by linking it back to the avail pointer. This ensures efficient reuse of array locations, preventing memory waste and fragmentation. Unlike pointer-based linked lists, cursor-based deletion avoids dangling pointers because all link management occurs through integer indices. Displaying a cursor-based linked list involves following the cursor values beginning from head and printing each node's data until reaching the end of the logical chain. This display operation provides a clear view of how the nodes are linked and is helpful for debugging. Since the nodes are stored within a fixed array, display functions often include index values, data fields, and cursor fields to help visualize the structure. This debugging advantage is often desirable in academic or restricted programming environments. One of the primary advantages of cursor-based linked lists is that they eliminate the need for pointers, making them safer in environments where pointer misuse can lead to system crashes, memory corruption, or security vulnerabilities. The fixed-size array also guarantees deterministic memory usage, which is vital in embedded systems and real-time applications. Furthermore, memory fragmentation is not a concern because all nodes exist inside a contiguous block of statically allocated memory. The management of the free list ensures that previously used nodes can be recycled efficiently. These factors make cursor-based linked lists reliable and predictable in memory-constrained environments. However, cursor-based linked lists also have limitations. Since the underlying array is fixed in size, the linked list cannot grow beyond the predefined capacity. This restricts their use in applications where dynamic or unpredictable memory growth is required. Additionally, although memory locality improves traversal speed, insertions and deletions may require more bookkeeping compared to traditional linked lists. The reliance on indices rather than pointers can also make the code slightly more complex to understand for beginners. In summary, a cursor-based linked list is a robust, pointer-free data structure that simulates the behavior of a linked list using array indices. It supports dynamic operations such as insertion, deletion, and traversal while ensuring safe and efficient memory management inside a fixed memory block. Its hybrid nature, combining array storage with linked traversal logic, makes it particularly suitable for restricted or educational environments where pointer usage is limited or undesirable. Understanding cursor-based linked lists helps learners appreciate the flexibility of linked structures while gaining deeper insight into memory management, indexing, and static dynamic simulation techniques.